Okay, let's look at some of the questions from chapter 7. So it's like algebra, polynomial division, factor theorem, and proof, I believe. So first things first, the basic stuff. If you've got any kinds of polynomials in fractions, then the first thing you're going to want to do is check to see if they factorise and cancel. Sometimes they will, sometimes they won't. But let's have a look at the bottom one first. So 6x squared minus 33x plus 42 factorises to, if it says 7 over 2, that means it's going to be 2x minus 7. So let's put on the bottom of the fraction 2x minus 7 and x minus 2. Always be careful. This obviously doesn't times together to make 6x, so there's also a factor of 3 there. You can check it. 3 times 7 times 2, 42. 2 times minus 2, and minus 7 times 1 is 4, and 7, which is 11, times 3 is minus 33. And then on the top, we can take out a factor of x, because there's no constant, and then factorise the rest of it like a quadratic. So again, 6, 3, minus 84. And we get 2x minus 7 again, and x plus 4. So again, there's the 6 that factorises out a 3, because there's only 2x squared there. So the 3's are going to cancel, the 2x minus 7 is going to cancel, and we're going to be left with x plus 4 over x minus 2. So that's A is 1, B is 4, C is minus 2. And then moving on to the factor theorem, so something that's a bit more A-level. To use the factor theorem, here you would just substitute in x equals 1 into this equation. So 4 lots of 1 cubed minus 3 lots of 1 squared minus 1. And if this is a factor, then this will become 0. So 4 minus 3 minus 1 equals 0. So that's the factor theorem. You can use it either way. You can either show that something is a factor by substituting in this case, x equals 1 is just whatever the opposite of that number there is. So whatever makes the bracket equal to 0. Substitute that in, and the answer comes out to be 0, then it is a factor. Or you can do it in the opposite direction. If you know that something is a factor, then you know that they add up to 0. Or if you substituted that in, it would equal 0. You could do that with the other ones. They'll all add up to 0. Given, this is what I was talking about, given that something is a factor, find the value of A. So if we know that that's a factor, then we know that 5 lots of 1 cubed minus 9 lots of 1 squared plus 2 lots of 1 plus A must equal 0. So that's 5 minus 9 plus 2 plus A equals 0, which gives us 5 minus 9 is minus 4 plus 2 minus 2, so A must be 2. Similar thing with this. It's a little bit more complicated. They've given us 2 things that are factors, and we've got 2 unknowns. So we're going to do the same thing twice and get simultaneous equations. So substitute in 1. So p lots of 1 cubed plus q lots of 1 squared. When it says show that, especially with these ones with the factor theorem, you've got to show all you're working out. So it looks obvious. You can't just write equals 0 at the end. You want to show more stages of working out than you might normally show. So that's why I'm putting in the 1 to show what I'm doing. That equals 0, which gives me p plus q minus 3 minus 7, so that equals 10. And then on the other one, I'm going to substitute in x equals minus 1. also equals 0 because we're given that that's a factor. So that's minus p, that's positive q. And then this would be minus 3 times minus 1 is 3, minus 7 is minus 4, take it to the other side. And then you can either solve those just like algebraically. It's relatively easy, you just add them together, you get 2q is 14, so q is 7, and p plus q is 10, so p is 3. Or you can use, if it's slightly more complicated, the simultaneous equation solver here. It always comes up x and y, so I'm going to use p and q in that order. That's why I've written it like this. P first, then q, then a number, so that it looks like this. 1p, 1q is 10, minus 1p, 1q, 4. So x is 3, I've put p in as my first one, so p is 3, and y is 7. So, same use. Knowing that they're factors means that when you substitute in whatever makes the bracket 0 for x, then the answer comes out to be 0. Okay, a bit of an easy proof. Now, no proof is really easy, but these are the easiest ones that you'll find. So, if something there's not, in some cases there's obvious things to do with proof, and in other cases it's not so obvious what to do. The more you do, the better you'll get. But I think it's not on the board. There you go. If something factorizes, you're going to factorize it. That's kind of a given. So n minus 1 is how that factorizes. We're trying to prove that that is even for all values of n. So how do you do that? Well, we're basically done with the algebra now. Just say if n is even, then we're doing an even times an odd, which makes an even. And if n is odd, then n minus 1 is even. And then again, odd times an even is an even. Essentially, we've got two consecutive numbers. One of them is going to be even. And if you times an even number by another whole number, you get an even number. Prove that when n is an integer between these values, then m equals n plus 2 is not divisible by 10. So when they give you a small range of numbers, then you're going to do proof by exhaustion, which is the most basic kind of proof that I can think of. You just do it for every number and show that it's true. So this is how most people start doing proof. And it builds to proving it's true for all numbers, which you can't do all numbers because there's an infinite number. So anyway, put 1 into this. 1 plus 2 is 3. It's not divisible by 10. Yeah, not a ball, put a 10. Then 2 plus 2 is 4. 3 plus 2 is 5. 4 plus 2 is 6. 5 plus 2 is 7. And 6 plus 2 is 8. None of these numbers are divisible by 10. And so that is the proof. There's no more to do because it's just show that if you put these numbers in for n, then m isn't divisible by 10. None of these numbers are divisible by 10. We've done all of them, hence proof by exhaustion. Same thing you're going to do here. Prove that every odd integer between 2 and 26 is either prime or a product of 2 primes. Do that for every odd integer between 2 and 26. So 3, 5, 7. You've got to do it for every one, but when you get to the end, you've proved it by exhaustion. Find a counterexample. Counterexamples are used for disproving statements. So you've got to find something where it's true. So if n is a positive integer, then n to the power 4 minus n is divisible by 4. So we're trying to find something where n is a positive integer that's not divisible by 4. So what if we put in, say, 3, what would come out? I did 1 in my head. 1 take away 1 is 0. 0 is divisible by 4. It's 0. 2, I imagine, would also be divisible by 4, but maybe not. 2 to the power 4 is 16. Take away 2, well, that's the answer then. 16, or 2 to the power 4 minus 2 is 16 minus 2, which is 14, which is not divisible by 4. So you're just looking for an example where it's not true, because we're disproving statements. Integers always have even number of factors. You just got to find one with an odd number of factors. You're looking for a square number. Square numbers have an odd number of factors. 2 squared, 4 would have a 1, 2, and 4. That's an odd number of factors. 2n squared minus 6n plus 1 is positive for all values of n. Now, if you do a little sketch, you know how much I like sketches. If you do a sketch, you'll find the minimum point is going to be below the axis. So polynomial, let's put it in 2 minus 6, 1. Crosses at 2 points I don't care about, but the minimum point is 3 over 2 minus 7 over 2. So 3 over 2 minus 7 over 2. So choosing a choosing a value of n where it's not positive I would just use that number, or any of the numbers between the two roots. But this seems like an obvious one, or just the number 1. So 2 take away 6 plus 1 minus 3. This is a multiple of 3 for all integer values of n. We have to find one where it's not. So sometimes you can just try different numbers, starting at, 0. 0 take away 0. Minus 4 is not a multiple of 3. So there we go. You just try different numbers with those. You're looking for one where it's not true. Moving on to intermediate stuff, writing each polynomial in a form this by dividing, you're just going to have to do polynomial division. So I'll do a couple in case you've forgotten the process. You write it, like you were in primary school almost. And then you divide the biggest degree of the polynomial, so x cubed, by the biggest degree of what you're dividing by. So x cubed divided by x is x squared. Write that above where the x squared is. It's like place value, but with degrees of a polynomial rather than powers of 10. And then you multiply what you've got by the thing you're dividing by and take it away. So x squared times by x plus 1 is x cubed plus x squared, and then take it away. Now that's a sticking point sometimes, because when things are negative, it's not obvious, or it can cause issues. If you're thinking about other things and you haven't practiced enough, then you can accidentally add instead of taking away. But 6 take away 1 is 5. Maybe there'll be some later where it's negatives. Then do this divided by that. So 5x squared divided by x is 5x. The reason you do that is so that when you multiply it out, then you're trying to cancel each one in turn. So you're going to cancel out the cube term, then the square term, then the x term. You're trying to make it simpler and simpler, like you would do in normal division. So 5x times x plus 1 is 5x squared plus 5x. Take that away, and this one always cancels, and then 3x plus 3 divided by x is 3. Just check that all becomes 0, which it does. 3 times x plus 1 is 3x plus 3. All becomes 0. And then, to write that, each polynomial in that form, then this is the quadratic part. So the second bracket, x squared plus 5x plus 3. And then x plus or minus p. That's just literally what you divided by. So when you divide it, you find the two factors. This is one of the factors. This was the other factor. Let's do this one because it looks like it's got some minuses in it. Maybe we'll have that minus thing happening. 4x cubed plus 9x squared. Drawn it on the top line. I'll make do. Divided by x plus 2. So 4x cubed divided by x is 4x squared. Multiply that back out. So x squared minus 3x minus 10. I mean, nothing subtracted there, so I'll just write it. Now it's one simpler. Divide by x again. So what's that? That's plus or minus. X times x, x times 2. This maybe would cause issues. It's minus 3, take away 2, so minus 5. Sometimes you know it's going to be a factor. You know, you've just worked it out using the factor theorem, for example. You know it's going to be a factor. So if it comes out to be not a factor, as in there's a remainder, check your negatives before you check anything else. You want to check that when you're doing the subtractions, especially with negatives, you're doing that right. There's more, obviously. I mean, it gets a little bit ridiculous. This is like practicing too much. It's going past the level that you're going to be required to do, so that you know for sure that you are capable. So this one, 6x to the 5 divided by 2x is 3x to the 4. Multiply it back out. 3x to the 4 times 3 is 9x to the 4. If you can do these ones, you know, you can do polynomial division. 13 take 9 is 4, and then all of this. Seems unnecessarily long. I think it probably is. 4x to the 4 divided by 2x is 2x cubed. So times that out again. 4x to the 4, 2x cubed times 3, positive 6x cubed. Take it away. Minus 4, take away 6. That bit there is the most important step to pay attention to. That times 15 minus 15x squared. Now minus 9 take away minus 15 is 6. Now we want 3x. So 6x squared plus 9x. Take that away. 21 take 9. And then we have 6. So it's a lot of doing the same thing repeatedly. Pay particular attention to this subtraction step and you'll be okay with some practice. Find the remainder. What the remainder is if this doesn't this isn't the same at the end, then that's not a 0, that's the remainder. The bits that follow on from that will be using the factor theorem first, and then showing that there's only one real root. So the way that you do that, use a factor theorem to show that that's a factor, as in put in x equals 4, show that it equals 0. And then, for the second part, divide by x minus 4, in the same way you've just done all that polynomial division, and the quadratic that is left will not have real roots, because we already have the only real root, which is 4. It says that's the only real root, so if it has the quadratic that's left has no real roots, as in b squared minus 4ac is less than 0, then that's proof. Okay, so the majority of those 4 marks come from doing polynomial division, and then the last bit is that the quadratic has a negative discriminant. There's a couple of those questions. This one has same factorise it completely and then solve it, as in that one's probably going to have 3 solutions rather than just 1. All cubics have at least 1 because they go from positive So from negative infinity to positive infinity. So they have to cross the x-axis at least once, possibly 3 times. Right, moving on to the more difficult proof style questions. This one, prove that, it says to use completing the square, but if you're ever trying to prove that something is positive for all values of n, it's almost always a quadratic. All you've got to do to prove that it's always positive is complete the square, as it tells you in this question, but it might not tell you in an exam question. So complete the square on it. N squared minus 4 over 3 n. Let's see if we can remember how to do this. Then I should have used the square brackets, shouldn't I? Because otherwise I'll forget. Let's do it now. N minus 4 over 6. Is that right? Yeah, 2 over 3. Squared minus 2 over 3 squared is 4 over 9. Plus 10. We don't really need to do much more. In fact, multiply it back out. So let's change that to 2 over 3 now. Squared. That times 3 is minus 4 over 3 plus 10. 26 over 3. And then your final part of this, so you've completed the square, the final part of it is to say that this bit is always greater than or equal to 0. So the smallest any square can be is 0. It can never go negative, because if you square a negative, it just becomes positive, and then this is positive. So it's always going to be positive, because 0 plus a positive makes a positive. Okay. Same thing here, but you're going to do it with the negatives, show that it never goes above the axis. I'll do that. So take out the minus first. So you've got n squared plus 2n plus 3. I don't know why I've taken out the 3. Let's treat it like a normal one again. Minus n plus 1 squared minus 1 minus 3 minus, put the things back in, so n plus 1 minus minus 1 is plus 1 minus 2 minus 2. And here that's always negative, so that's always less than or equal to 0. Okay, because this part, the bracket squared, is always positive or 0. Make that negative, it's always negative or 0. Take away 2 from that, it means it's always going to be less than or equal to minus 2. So that's your proof. Maybe write a sentence. There's another one there. All I'll do is move the 4 to the other side and do the same thing. This one, prove that it's got, given that it's got no real roots, prove that the k satisfies this inequality. No real roots is b squared minus 4ac is less than 0. So that's what you're looking for. There's the extra bit of it being above 0. That's necessary because if it's actually let's do this question, because it looks like maybe it's got some things that are a little bit more tricky than I am giving it credit for. So firstly, let's do b squared minus 4ac is less than 0. So b squared minus 4 times a times c is less than 0. That gets us 25k squared minus 12k is less than 0. Okay, so now I understand. You factorise this. So let's do a sketch, shall we? If we know that it's got to be less than 0, we're going to go through k equals 0 and 12 over 25. So that's where the two values come from. K equals 0, k equals 12 over 25. Those are going to be my roots. So the bit where it's less than 0 is between k equals 12 over 25, and k equals 0. Now don't just look at this and go, oh, I'm just going to put that in, because the 0 is not, we haven't got there. All we've done is we've shown that it's between 0 and 12 over 25. To get the 0, let's just look at what happens if k equals 0. We have 0 plus 0 plus 3. That's just the line y equals 3, which is not a root. Okay, so let's do that separately. K equals 0. Then we get 0 plus 0 plus 3 equals 0. So that's clearly not true. So k is not equal to 0. If there's a root, if there's a root, k is not equal to 0. So it tells us there's no roots. So we're going to include k is not equal to 0. As in, we're going to include k equals 0 in the bit where there's no roots. Because if k equals 0, then you don't get a root. Prove that the difference of two squares of consecutive even numbers is always divisible by 4. So to do that, we'll have to define some things. So consecutive even numbers, let's start with that. Let's have our first consecutive even number as 2n. 2 because it's got to be even, and then n because 2 times by a number makes it even. And then the next one is 2n plus 2. These are our two consecutive even numbers. How do you spell consecutive? Like that. Even numbers, it's in the question. Prove that the difference of the squares of two consecutive even numbers is always divisible by 4. So let's just put here that is integers. So we've got square them, 2n plus 2 squared, and 2n squared, and find the difference. So difference of the squares. These are my consecutive even numbers. That's them squared, and then the difference of them. And we're trying to show that that is always divisible by 4. So let's do a bit of algebra. So 4n squared, 2 times 2 times 2, 8n, 2 times 2, 4, minus 2n squared, which is 4n squared. Those cancel, and we get 8n plus 4. Now to show that something is a multiple of 4, or divisible by 4, I would recommend taking out 4 as a factor. If everything inside here is an integer, then you can, that's a proof, right? If everything inside there is an integer, then it's 4 times by an integer, and that is therefore divisible by 4. Is it true for odd numbers? Well, the answer is going to be no, I imagine. But let's do it. We'll do two consecutive odd numbers, so 2n plus 1, 2n plus 3, or 2n plus 1, 2n minus 1, something like that. Do the same thing. 2n plus 3 squared, 2n plus 1 squared, expand, 2 times 3 times 2, 4n squared, 2 times 1 times 2. We're taking away all of that. 4n squared take 4n squared. 12 take 4. Oh wait, it is true. So 9 take away 1, 8, which is again a multiple of 4. Even if you can take out a multiple of 8, don't, because you're trying to prove that it's divisible by 4. So it is also divisible by 4. Interesting. Okay. Then it moves on to the exam questions. For these, a lot of them are going to be the same, so as the ones we've done, factor theorem, and then show that it's the only real root, so put the value of 3 in, show that it equals 0, then divide and show that the quadratic has no real solutions. This one, factor theorem again, find the constants by division, hence show that it's only got one real root, same kind of idea. You can see there's some repeated things. This one, write down the real root of this equation. If you've only got one real root, x minus 5 just means that that x value increases by 5. It moves to the right 5. So whatever you get here, add 5 for that d part. Prove something is a factor, factor theorem. Hence, using algebra, find its roots. So polynomial division, they are repeated. Let's have a look at this last one. Figure 2 shows a sketch of the curve with equation y equals f of x. So that's the original equation. Deduce, giving reasons for your answer, the number of real roots of this equation. So note the difference, or the only difference is that's the same, that's the same, that's the same. It's the 48 that's different. This is 48, this is 46. So what it means is to get from this equation, the one that's drawn, to this equation, we're going to have to go down 2. Okay, so this down here, this is f of x, close brackets, minus 2. So it's gone down 2. So to do that, you take the whole graph and move it down 2. So how many solutions is it going to have? 1. And then this, instead of being just touching it and bouncing off, there's going to be 2. It's going to cross over. So there's going to be 3 solutions. 1 there and 2 there. Given that k is a constant and the curve passes through the origin, find the possible values. We talked about this again with chapter 4. You want to kind of move it to the left by, I mean, I don't know what the solutions are, but you should get a solution. Whatever that solution is, that's going to be one of the values of k, and then the other one's going to be 4. Because you want to move it left 4, so add 4. And then there's a lot of similar things. You see there's transformations, fits in nicely with this, because most of the time you're factorising something and then you can sketch it really easy once it's factorised. Similar ideas. I'm looking for something which is a bit different. Remainders. Okay, this I will talk about. You'll see this kind of thing. N is a natural number. Quite a few times. It'll either be written as it's a natural number or it's a positive integer. They're the same thing. A natural number is just all the numbers 1, 2, 3, 4, 5, starting at 1 and going up. See again, natural number, positive integers. So this is the way, it's not really in the textbook, but in the exams it's very common. So let's do one of these to show you what you would do anytime you see this. You should firstly consider splitting the numbers into odd numbers and even numbers. Okay, so for this one, you're going to go, if n is a natural number, what if n is even? So I can't use n as my letter here, so I'm going to use k, 2k, where k is an integer, n is therefore even. So if n is even, then n cubed plus 2 is 2k cubed plus 2, which is 8k cubed plus 2. Now this, not divisible by 8. Okay, because it's got a part which is divisible by 8 and a part which is not. So if that's true, if you've got a number which you can split it into a bit which is divisible by 8 and a bit which isn't, then the whole number isn't. You know, this is 8 times by a number, multiple of 8 plus 2. If you add 2 to a multiple of 8, you do not get a multiple of 8. That was the even numbers, then do it for the odd numbers. Exactly the same idea. 2k plus 1 cubed plus 2. You're going to have to use the binomial expansion actually there. So 2k cubed is 8k cubed plus 3 lots of 2 times 1. So 6k squared, and then 3 lots of, oh no wait a second, that's 12, because that's 2 squared. You don't actually have to use the binomial expansion, you could just expand it old school. This one's 6k. Add 1, add 2. I mean, this isn't even. This isn't even. This is 8k cubed, so even, odd. If you add 3, this is not divisible by 8. It's not even. So all of the questions which have this kind of thing, positive integers, split them into odds and evens. Okay, that's that for that one. Enjoy.